Hi there, and welcome to this lesson on Pure Mathematics 3 from the Edexcel International A-Level. We're on Chapter 2, Functions and Graphs, and we're up to 2.2, Functions and Mappings. Now, I think I'll confess at the very beginning, mappings, I am not a big fan of them. They're not something that I would ever choose to use, but they're in the syllabus, so we've got to do them. First of all, just think a little bit about language of functions. There are two very common notations for writing functions, and one notation which is rarely used, but it's in the syllabus, so we've got to do it. They all mean essentially the same thing. There are subtle differences, but for most purposes, you can regard them as identical to each other. They're just different ways of thinking about the same concept. So, for example, the language you'll be most familiar with is comes from Cartesian geometry, something like y equals 3x minus 5. You should also be familiar with function language. F of x equals 3x minus 5. And that is how you would read that, f of x. What we also need to consider now is what is called mapping language. And the way you would read that statement is f maps x to 3x minus 5. Don't look for the difference in these things. They really are basically saying exactly the same thing, but in three different ways. The idea of a mapping is probably the most general of the three ideas. You have a set of numbers that you input into the mapping, and they're transformed into an output set of numbers. So, for example, if you had the mapping f maps x to 3x minus 5, the number 2 would be a possible input to the mapping, and f would map 2 to 3 times by 2, take away 5. Exactly as you would do with a function, exactly as you would do if you had y equals 3x minus 5. The output would be 1, 6 take away 5. Now, a mapping can be one of three different types of things. This sometimes feels a little bit confusing, but the concept is important and does turn up on the exam. A mapping can be one-to-one. If it's one-to-one, there is exactly one output for each input, and vice versa. A mapping can be many-to-one. That means different inputs may have exactly the same output. Or the other way around, a mapping can be one-to-many, which means one input could have different possible outputs. Now, this last case is a bit of a problem and does matter. It's one to bear in mind. It doesn't feel good when you say it. So you put a number into the function, and you don't actually know what's going to come out. There are different possibilities. Three examples. I'll let you have a go at doing these first, and then I will talk through them. So have a go. Describe each of these mappings either as one-to-one, many-to-one, or one-to-many. Pause the video and then come back when you're ready. Okay, we'll go through these together. The first one, f maps x to x squared plus 3. This is a many-to-one function. Different inputs can have the same output. So for example, if you put 2 into this function, then it would map to 2 squared, which is 4, 4 plus 3, which is 7. But if you put minus 2 in, exactly the same thing happens. Minus 2 squared is also 4, 4 plus 3 is 7. That's what many-to-one means. Two different inputs, but you get the same output. The second question, f maps x to 7x minus 4. This is a standard function. This is a one-to-one function. There is exactly one output for each input and vice versa. Now, it's worth just explaining what that means. It means, for instance, if we put in x equals 2, there is only one possible output. And in this case, it would be 7 2s are 14, take away 4. The output would be 10. The vice versa bit, that means if we chose an output, let's say we chose 10, and we ask what the input was, again, there is only one possible answer. So putting in 10 as the output and finding the input That is what you would normally do when you're solving a linear equation in this case. Exactly the same. So 10 is the output. The input will be the value of x. We're solving the equation. That would give us 7x equals 14. That would give us x equals 2. And that is the only possible input which will give an output of 10. That's what one-to-one means. There's one output for each input. There is one input for each output, both ways around. And the third question, f maps x to 10 plus or minus the square root of x. The plus or minus should start ringing alarm bells with you. This is a one-to-many function because one input for x can have different possible outputs. If x equals 9, so if 9 is the input, well, the output could be 10 plus the square root of 9, which is 10 plus 3 and 13. But the output could also be 10 take away the square root of 9, 10 take away 3, which is 7. That's what is meant by a one-to-many function. We put in x equals 9. We don't actually know which is the right output. Both are possible. Now, a quick aside here. It's a small point, this, but it frequently causes confusion. It even confused me just last week when I was looking at a particular question. If you write y equals x, there's no plus in front of the x, but you know it means y equals plus x. This is slightly less obvious and turns up in slippery ways. If you ever see y equals root x written down, exactly the same as above. If they write y equals root x, that means y equals plus the square root of x. I think the thing is, whenever you see square root, the first thing that goes through your head is it could be plus, it could be minus. Not in this case. If they write y equals root x, plus root x is what they mean. Now, if you want to make it clear that both the positive and negative values are possible for the square root, you have to write the plus minus. So if you write y equals plus or minus root x, then you are saying it could be plus, it could be minus. But without that, it is plus root x. For example, if you had to sketch the graph y equals root x, that is what it would look like. Just the positive value of root x. Whereas if you were sketching the graph of y equals plus or minus root x, then you would get what you would normally think of as the graph for that. You have the plus values on the top of the axis here, and underneath the y-axis, you have the negative values of root x. But you need the plus minus to get the whole graph. Okay, mappings, we've said, are written something like f maps x to 3x minus 5. The normal language for functions is something like f of x equals 3x minus 5. Now, as we said, they mean the same thing. I suggested that they're identical to each other. Not quite true. Not all mappings are functions. And this distinction that's coming up is very important, frequently turns up in the exam. For a mapping to be a function, every input must have an output. That's the first thing. But more than that, it can only have one possible output. So every input must have an output. There must be something that comes out that's acceptable, and only one thing can come out. So for example, the function we were thinking about just now, f of x equals plus or minus the square root of x, that is not a function. Why not? Because each possible input, like 4 for example, has two possible outputs. Could be plus 2, could be minus 2. So every input does have an output, it obeys that rule, but it does not obey the second rule, that it has only one possible output. Now, if you draw the graph of y equals plus or minus root x, we had it just now. One way to tell if you have a function is to consider drawing a vertical line through the graph. If a vertical line can cut the graph in more than one place, you do not have a function. because you're having two possible outputs for one possible input. For instance, if you look at 3 here, we drew a vertical line at 3, we get one possible output there at plus root 3, and we get another possible output there at minus root 3. But that's the thing you should look for with the graph. If a vertical line cuts the graph more than once, it is not a function. Now, if we just have y equals root x, and as we said, that implies plus root x, we don't get the minus bit. A vertical line now can only ever cut the graph once. We do have a function, or at least we nearly do. We've solved one problem. We don't get two solutions now. We do just get the one positive solution for every value of x that we put in. However, as we've stated things so far, we haven't really thought about what's happening over here on the left-hand side. If you have negative values of x, the graph never reaches over there. That's because you can't square root a negative number. Now that matters because we haven't said that you couldn't put a negative number into the function, but you can't. So until we do something about that, we have another problem, which is that not all numbers work in the function. Positive numbers work fine. Negative numbers do not work. You can't square root a negative number. Now, this leads us to something very important. For functions, you must state the numbers that are allowed to be put into the function. And this set of numbers has a special name. It's called the domain of the function. The domain of the function is all of the values of x which are allowed. It's all of the numbers that you're allowed to put into the function. The way you describe the domain is by using set language. You may or may not have seen this before. That's an example of set language there. And the way you would read that very short statement is x is a member of the real numbers. That just means x is a normal number. Nothing really weird is going on. But x is one of the normal numbers that you're familiar with. This says something stronger. This says x is a real number. It's a normal number. But more than that, it's a real number which is greater than or equal to 0. So you're saying exactly how big or small it can be. Now, if you go back to what we were saying before, the square root of x as a function, it had two problems. If we say, first of all, only plus the root of x, and secondly, we say x has to be a real number which is positive, greater than or equal to 0, this does obey the strict rules for a function. So coming back to the graph, if we write y equals root x and we specify this domain, now it's fine. There's no negative bit down here, so we don't get two answers for the same input. And this negative bit over here on the x-axis, it's not a problem because we've said it's not a problem. We've said x has to be a positive number in the domain of the function. Okay, second set of examples for you to have a go at. Bearing in mind what we've just said, try and decide which of these four functions are functions. Which of them keep the rules for being a function? Pause the video, have a go, start it again when you're ready. Okay, first question, f of x equals 2x squared plus 5, where x is a real number. Well, yes, this is a function. There's no problems here. There is exactly one output for every possible input, and all the numbers where x is a real number, they're all fine. None of them are an issue. So yes, this is a function. Second question, f of x is equal to 4x plus 1 over x, where x is a real number. No, it's not a function. There is a problem with this function if x equals 0, because you can't divide by 0. The more formal way you'll see that written down normally is that division by 0 is undefined. But the bottom line is that x equals 0 is a problem, and you can't put it in that function. So there is not an output for every input. If you input x equals 0, there is no output. For that reason, f of x is not a function. Third one, f of x equals 4x plus 1 over x, where x is a real number and x has to be bigger than 0. Well, if you say x has to be bigger than 0, that gets rid of the problem. The only problem was when x equals 0. Every other real number is fine. So yes, if we add that restriction, we do now have a function, and there is exactly one output for every possible input. It would also be acceptable to say f of x equals 4x plus 1 over x, where you just say x can't equal 0. Just rule out the one number that isn't allowed. That also would be fine, and that would be a function. Every other value other than 0 isn't a problem. The fourth one immediately looks a little bit dodgy. 3x squared plus or minus 5 times by root x. No, this is not a function. No problem with negative numbers here. We've said x has to be positive. So it's not that there's a problem with x being negative and square rooting a negative number. That isn't the problem. The problem is the plus minus. Each input permits 2 possible outputs. One with the plus sign from here and one with the minus sign from here. Therefore, f of x is not a function. Domain and range. So we've already said that the domain is the set of numbers that are put into a function. It's the values which x is allowed to take. And I think that's the easiest way to think about it. Domain, that's the values of x allowed, the values you put in. The range is the set of numbers that come out of a function. It's the output of the function. And the range is all of the values of y which are allowed, all the values of y which the function produces. For example, if we had a function, x squared plus 3, say, with domain, x can be any number you like, and we wanted to know what the range of that function was. Well, what we want to know is all the values that y can take. A sketch helps a lot to show what is going on. So there's a sketch of f of x equals x squared plus 3, with domain x is a real number, any real number. To work out the range, what we're asking ourselves is, what values can y take? Looking at the graph, it's obvious. Y comes down to 3, then goes back up again. It never ever comes below 3. The range is f of x has to be bigger than or equal to 3. And when you write the domain, you'll notice you say what x has to be. When you write the range, if you're using function language, you have to say what f of x has to be. If you get confused, just remember f of x, y, they essentially mean the same thing. What can y be? What can f of x be? Same statement. Any number bigger than 3 in this instance. Okay, 3 questions for you to have a go at. I warn you now, the last question is very hard to do. The sketches are tricky and the logic is tricky. But have a go yourself. And then when you're ready, restart the video and I'll go through these 3 questions with you. Okay, we'll have a look at these. So we need to sketch the function and then find the range. That was the first question, f of x equals x squared. And we've been told the domain. The domain is x has to be between -4 and +4. That's what it should look like, the red curve starting at -4, going all the way through to +4. That's f of x equals x squared. That's the domain. We've been asked to find the range. The range is the values that y can take within this range of values here. Now, y starts up here at 16, comes down to 0, and then it goes back up to 16 again. But that's the spread of y for this function. Goes up as high as 16, goes down as low as 0. That's what you have to write down. So the range is f of x has to be bigger than or equal to 0. It's got to be less than or equal to 16. And that would be just writing it in normal language. Y has to be bigger than or equal to 0, or less than or equal to 16. Second question, f of x equals 1 over x, where x is a real number. And again, they tell you that x has to be bigger than 0, which is a good job, and less than or equal to 5. First thing you do is do a sketch. That'll be the sketch. So it's heading towards 0, up and up and up. Can't see the top of the graph. And then we're moving towards x equals 5. That is the last point, because it tells us 5 is the last point. We're starting just above 0, and we're finishing at 5. We've got to find the range. The range is the values that y can take. Well, y goes up and up and up indefinitely, so there is no biggest value of y. But there is a smallest value of y, and it's there at the very end. The smallest y ever becomes is 0.2 or 1/5. That's the range. So the range is f of x or y has to be bigger than or equal to 1/5. It's never less than it, and it can be any value bigger than it. That's the way you'd write it down. Okay, this third question, I was reluctant to do it, but there are questions like it in the textbook, and I think questions like it may well turn up on the exam. They've done something quite confusing here. They've given you one possible function for x less than 1, and then a different function if x is bigger than or equal to 1. So it's two things that you're going to have to combine together. Doing the sketch is quite a lot of hard work for this question. I'll show you it. Now, I've got numbers all over the axes here, but that's just because of the graph drawing package I was using. If I was doing this myself, I most certainly would not have axes with numbers written on it. I would be doing a sketch of 5 minus 2x, which I know crosses the y-axis at 5, so I'd make a mark there. It's coming downhill because it's minus 2x, and stretching forever in that direction. But it's got to stop when you get to 1. So you put 1 into here. 5 minus 2 is 3. So it's going to stop there, where y is 3 and where x is 1. Then you've got x squared plus cubed if x is greater than or equal to 1. The starting point is 1. Put 1 in here, and then you'll know where it's starting from. 1 squared plus 3 is 1 plus 3. So it's going to start at 4. 1 plus 3 is 4. That's the starting point. And then it's got the general shape of a quadratic heading up after that. But that's all I'd be doing, a sketch, no axes. I wouldn't actually have done an accurate axis for any of the questions that we've been looking at. I'd just be doing a sketch and marking key points that matter. In this case, the 5 matters. That point matters at the very end of the line. That point matters at the very beginning of the curve. Now, that's all complicated. What is simple is what we've been asked to do, which is work out the range. We're combining these two functions together, and we're saying, what can y be? Well, there's no limit to how big it can be, and it can come down and down and down until you reach that point. Never gets less than that, but it can be any value bigger than that. So any value from 3 upwards would be acceptable. Now, I think I've actually made a mistake here. It's a small mistake, but you would lose a mark for it. Looking at the red line, 5 minus 2x, it doesn't actually reach 1. It says here, we're doing that if x is less than 1. If x equals 1, we're on the curve. Now, sometimes that's shown with like a little hollow circle and a solid circle to show that the endpoint is allowed or the endpoint isn't allowed. Maybe it would have been good if I'd done that. But the endpoint on this red line is not allowed. It says we're only on the red line if x is less than 1, not if it's equal to it. Now, have I done it wrong? Have I not done it wrong? The range is f of x has to be greater than or equal to 3. It can't equal 3 because you can't actually be on the very end of the line. That's what this is saying. It means this greater than or equal sign here is wrong. It is a mistake. The range should be f of x has to be greater than 3, strictly greater than 3, because it can't actually equal the point on the end of the line. I hope that makes some sense. Okay, that gets us to the end of this section. If you have the textbook, go to page 18, have a go at exercise 2b. Thank you very much for watching, and that is indeed the end of this lesson. Cheerio.